So Beam is a mission-driven company. We are committed to creating lifelong cures for patients suffering from serious diseases. And we really believe that this goal is now in reach as an industry based on the incredible progress being made by the gene therapy and gene editing fields, and more specifically using the technology that I'm going to tell you about today. We were founded by three of the pioneers in the gene editing field, David Liu, Feng Zhang, and Keith Jung. Many of our early employees joined us from their labs, and they include several of the inventors of the technologies that you'll hear about today. The team is now over 100 people, growing rapidly, united by the values you see here, and sharing a passion to make a transformative impact on patients' lives. So to summarize, Beam really represents the next generation in gene editing. So first, we're using novel, potentially best-in-class gene editing technologies. First and foremost, this technology called base editing. So what base editing allows us to do is to make single base changes, single letter changes in your genes, turning an A to a G or a C to a T, doing it with very high efficiency and precision, but without cutting the DNA. We've paired that with additional complementary editing platforms, including a nuclease family, RNA-based editors, and the recently published prime editing. We're building directly on the advances that have been made in gene editing over the previous years, and that's going to let us go faster and reduce our risk. Base editors do use CRISPR for gene targeting, which gives us advantage of taking advantage of the validated approach to gene targeting that CRISPR represents. And in delivery, we're using clinically validated delivery modalities that have already generated proof of concept in humans, and in some cases, approved products. Things like electroporation, lipid nanoparticles, and AAV viral vectors. The platform is very versatile and very modular. This means we have a lot of different applications we can create. First and foremost, we can correct point mutations. Point mutations are the most common class of genetic change driving disease, a single letter misspelling. And that's a perfect application for a base editor to go into that letter and turn it back to something that's normal. That said, we can also modify genes, silence genes, reactivate genes. We can do single edits, or we can do what's called multiplex editing, where we make several edits all at once in the genome. The modularity of the product engine is really incredible as well. Once we've engineered a base editor to go after a given disease, with a very simple change to the construct, we can retarget that editor to an entirely different spot in the genome, meaning it can treat a different disease, a different patient population. And we can do that potentially again and again. This has already been applied. So at this point, we have a very diverse, broad portfolio of about 12 programs, all still wholly owned. Most recently, we published in vivo proof of concept base editing blood cells for sickle cell disease at the end of last year, a result that I'll walk you through today. And 2020 promises to be even busier. So we're going to have additional in vivo proof of concepts from elsewhere in the pipeline, followed by progression into IND-enabling studies this year. And if we do that, that would set up a potential wave of IND filings beginning in 2021 as we move to the clinic. So let me tell you a little bit why we're so excited about this technology. So all of your cells have about 3 billion letters in them. These are the bases of your DNA, A, G, C, and T, that form the code of life, and they encode for the functional proteins that cause the cell to do its functions. You also know that changes in that DNA can cause disease. Genetic mutations cause genetic disease or susceptibility to disease. So shown here, you have a point mutation. A G has turned into an A, which is causing a disease. So the grand challenge in gene editing is, how can we revert that sequence directly back to normal, back to something that is healthy? And we want to do that precisely, permanently, and predictably. So the state of the art to date, if we're trying to do this, is what are called nucleases. So of course, this begins in the late 80s with meganucleases, followed by zinc finger nucleases, TALENs, and then famously, more recently, CRISPR and ARCUS. So these are all very different technologies from each other, but if you step back, they're all making the same kind of edit. So they target a certain spot in the genome and they make a double-stranded break, or a cut. Once you make that cut, the cell will rush to put the pieces back together again, but it'll do so with damage, random insertions and deletions at the cut site. Those changes will disrupt and turn off that gene. But if you want to correct a sequence deliberately, you have to do something completely different. Here you do what's called homologous recombination, where you bring in a DNA template that has a corrected sequence, you make that cut, and you hope that the cell replaces the sequence at that target site with your corrected sequence. And this can happen, but it's a very inefficient reaction. The machinery required to do this is only present in dividing cells, not in non-dividing cells. And of course, most of your cells at any given time are not dividing. As a result, a good experiment with homologous recombination might only yield a low single-digit percentage of correction in the cell, whereas the rest of the time you just get that disruption approach. So that was the backdrop for the invention of base editing. And so in base editing, a series of scientists in David Liu's lab hypothesized, wasn't there a way to do this more directly? Can we go straight to the cause of the problem, this single letter misspelling, and convert it directly from one letter to another without needing to cut the DNA in the process? And this would be base editing, where now rather than having scissors for the genome, which is the case with nucleases, now we have a pencil. We can make a single letter change, erase what was there, write in something in its place. So it turns out with base editing, that's exactly what we can do. So this is what a base editor looks like. So it's a two-part system. We do use CRISPR for targeting, and we use it in exactly the same way that CRISPR normally works. So it's loaded up with what's called a guide RNA. This is a short nucleic acid sequence that encodes the address in the genome where we want the CRISPR to bind. What that means is simply changing the guide RNA from one to another gives us an entirely new medicine, because now we're going to target a different spot in the genome. And that's where we get that rapid extendability of this platform that I mentioned earlier. Importantly, we've changed the CRISPR so that it doesn't cut. It doesn't make that double-stranded break. And instead, it just binds. The edit is then rather made by the deaminase, and that's a next component that we've added into the system as part of this fusion protein. Deaminases are naturally occurring enzymes in the body that can chemically modify certain bases, depending on which one you use, from one to another. So it's a perfect application for base editing. Depending on which deaminase we use, we get one of two kinds of editors, either an A to G editor called the A base editor, or a C to T editor called the C base editor. These two editors alone turn out to be enough to correct over 60% of the point mutations driving human disease, as well as activating genes, silencing genes, and many other applications. The way it works is shown here. We bind the DNA. The CRISPR actually opens up the DNA, and one of the strands of DNA is exposed to solution as a single-stranded loop. And specifically, a window of about 4 bases wide is available to the deaminase for editing. So when we design these editors, we make sure the CRISPR can land in such a way as to present the base that we want to edit right in that window, and then the deaminase will take over and do it very efficiently. It's a chemical modification. It's very predictable and precise. The modifications are those you see on the right. Cytosine turns into uracil, which is read by the cell as a T, so that's C to T. Adenine turns into inosine, which is read by the cell as a G, or A to G. In some cases, if we want to improve the editing rate that we get with these editors, we actually have the ability to further tune these constructs so we can improve either the CRISPR binding or the deaminase activation, all of which are insights proprietary to Beam and are a big part of our know-how advantage. So the advantages of the system are numerous. So first, obviously, is the precision, our ability to make single base changes in genes, the predictability of that change. So we know not only where we're going to edit, but we know what we're going to edit the base and the sequence into. Compared to something like AAV gene therapy, this is also a permanent edit. So we don't worry about the cells having the signal wear off over time. If you treat a young kid with AAV, the edit or the gene will not pass on to the daughter cells as the organ grows. Here, the edit will be made in its normal place in the genome. It'll turn on and off regularly. If the cell divides, it'll pass on the edit to the daughter cells, and you won't have any worry about it turning off over time. So in many ways, an ideal kind of edit. In the middle, more importantly, it's very efficient. So because this is chemistry, once we bind, we edit very quickly. And as a result, you'll see editing results over the course of the talk at 50, 60, 70, 80, even 90% and up of precise conversion of one letter to another at the right location. And those are unprecedented editing rates when compared to something like homologous recombination using nucleases. And that's partially because we're active with base editors in both dividing and non-dividing cells, and we edit the DNA directly without needing to bring in a template. Finally, we do avoid some of the unintended consequences of double-stranded breaks in the genome. On target, that includes things like insertions and deletions at the target site, which of course we don't get because we're not breaking the double strand. And finally, if you ever make multiple edits in the genome using a nuclease, those simultaneous cuts can cause mistakes to be made while the pieces are being put together at the level of the chromosome. So you get what are called chromosomal rearrangements, which are clearly undesirable. Here, because we're never breaking the double strand, we don't have that issue. So a wide variety of reasons why base editing represents a really exciting next generation in editing technology. So once you can change any base in the genome, what would you do with it? So it turns out there's a wide variety of applications we're pursuing. First, of course, we do work on gene correction, going after point mutations that are causing disease, a single letter misspelling in your gene, and we want to turn that one letter back to normal. So a lot of the programs you'll see today, including programs in sickle cell anemia, alpha-1 antitrypsin deficiency, we're pursuing this sort of point mutation correction. Another application is called modification of genes. So we know a lot from clinical genetics about the natural variation in genes among human populations, often also variations at the single base level. We know that some of those populations are protected from disease. So what if we could take that insight and now install that exact point mutation into other patients to confer that same protection for them? We can reactivate genes. So if we go to the regulatory elements of certain genes, we can then de-repress them or make a change that causes them to come back on and express at a high level. Conversely, we can silence genes. We do that with several different changes, one of which would be to take several normal codons, these three-letter triplets, and with a single C to T change, we can convert it into a stop codon. So now we're telling the cell to turn that gene off, and we're doing it without needing to cut the strand. Finally, we can make any of these edits as a single edit, but we can also stack them on top of each other in what's called multiplex editing. And in multiplex editing, we do a single editing reaction, we put the editor into the cell, but now we're going to add multiple guides all at once. And those guides will independently load into the editors and search the genome and then edit in parallel. And because we're doing this without creating double-stranded breaks, we don't need to worry about those chromosomal rearrangements that would occur if we did this with a nuclease. So really exciting and broad set of applications to treat a very wide variety of diseases in new ways. So we're so excited about this technology as representing a really new and important option for patients that we're investing in parallel against all of the available delivery modalities in genetic medicine. So you're familiar with many of these: electroporation, where you take cells out of the body, you pass an electrical current through them, and then the editor goes in. That can be done to blood cells in the case of hematology, or immune cells, T cells, in the case of CAR T cells for oncology. We're using lipid nanoparticles to package these editors, and that will take us to the liver. And then we're using AAV viral vectors. You're very familiar with these from the gene therapy field to target the eye, as well as the CNS, and potentially many other places beyond that. In each of these cases, there are obviously clinical data showing this is possible, but even approved products with these sorts of delivery modalities. The idea here is to take risk out of the equation for us. We have a novel payload. We want to deliver it with high confidence using known technologies. Over time, we'll diversify, we'll push the boundaries of where we can go, but for now, this is plenty to work on. So this has resulted in the pipeline you see here. A very diverse set of programs that you can see. In each of these therapeutic areas, we have identified flagship programs that we're working on, which we think really show the differentiation of the base editor technology. In hematology, you can see our programs for sickle cell disease and beta thalassemia. Very active space in the competitive landscape here. We're able to do two things that others can't do. We can drive up levels of fetal hemoglobin to compensate for the disease, but we can do it more precisely and to higher levels than others are able to do. And then we're the first company pursuing an approach to directly correct the sickle mutation itself for the first time and eliminate it from the cell altogether. The sickle mutation is, of course, the most famous single mutation in all of genetics. On the cancer side, in CAR T, we're creating CAR T cells that now have many edits. We're taking advantage of that multiplex ability to silence many things on the surface of the genome without cutting, allowing in these products us to add up to 4 edits at the same time, adding more functionality and hopefully making these cells even more effective for patients. And then in vivo, back to the liver and the eye, we're again targeting point mutations to directly correct these disease-causing bases in these genes and turn them back to normal. So a very broad portfolio, all moving in parallel, and we are to make sure that we're not just choosing a few of these projects to work on, but really moving them in parallel and letting the best ones win over time. This means that once we begin to file INDs, we should have a sustainable pipeline to regularly move new things into the clinic. Furthermore, as any of these programs succeed and validate a given therapeutic area for our technology, we can quickly double down and bring on-deck targets forward to rapidly expand in that area. So now I'll walk you through some of these examples. So I'll start with the electroporation approach, ex vivo. So this is a typical editing result where we're electroporating blood cells to put in the editor and we see what happens. Of course, the untreated cells have no base editing, but on the right-hand side you can see the successful conversion at a specific target site of A to G at a single spot in the genome over 80% of the time. Okay, so that's that very high efficiency that I talked about before. Again, an unprecedented level of precise editing that would be out of reach for nuclease technologies using homologous recombination. So we're applying this in hematology, as I said, for sickle cell disease and beta thalassemia. So these are severe, chronic, inherited blood disorders. In the case of sickle cell disease, where you have a faulty hemoglobin that builds up in these polymers that actually causes the blood cell to distort, builds up in capillaries and causes these incredibly debilitating and painful crises for patients. In the case of beta thalassemia, the hemoglobin is just gone, and so you have an increased level of anemia given the loss of hemoglobin. So here we have these two complementary approaches. First, we're upregulating the fetal form of hemoglobin, which is normally turned off after about 6 months of life. But here we're going directly after the fetal hemoglobin gene and to reactivate it using these precise base edits, which would then be a therapy for both sickle cell disease and beta thalassemia. The second approach is, as I said, the first company to pursue the direct correction of the sickle mutation itself. The E6V mutation, every single patient has the same point mutation change. We want to go right in there and turn it to something that is normal to treat sickle cell disease. So I'll walk you through each of these examples. So first, for fetal hemoglobin, it turns out there is a condition called hereditary persistence of fetal hemoglobin, or HPFH. So patients who have this have specific point mutations in the regulatory region of their fetal hemoglobin genes that causes them to never turn off. So they maintain high levels of fetal hemoglobin throughout their lives. If those patients also happen to have sickle cell disease or beta thalassemia, it turns out they're protected. So it compensates for those diseases. So this is an example where we would like to give those exact mutations to other patients so that they will also have high levels of fetal hemoglobin and be protected. There's a lot of discussion in the field about a threshold for efficacy of raising fetal hemoglobin around the 30% range, and we think that's true, but it's also true that more fetal hemoglobin ought to be better. And as you increase the level of fetal hemoglobin, you'll further compensate in these cells. And so our goal is to do exactly that. So this very exciting result, I'll take some time to walk you through. This is the in vivo proof of concept that we published last year to show this robust induction of fetal hemoglobin. So this is a mouse model, but we're editing human cells. We edit them, we then engraft them into the mice, and we wait 16 weeks to make sure that those cells have really taken over in the bone marrow for the long term. So going left to right, you can see the human chimerism. That just means how many of these cells successfully engrafted in the mice. And you can see very high levels of engraftment for this process, over 90%. More importantly, you can see that our HPFH edited cells have equal levels of engraftment as the unedited cells, showing that our process was very gentle and the stem cells indeed received the right level of edits. In the middle, you can see the editing results. So here we've got over 90% editing of this specific A into a G, conferring these HPFH mutations. Of course, the unedited cells don't have any editing. And finally, the specificity of this edit shows in the induction of the fetal hemoglobin shown on the right. So here you can see a very robust upregulation of fetal hemoglobin, over 60%, of course not much in the unedited state, and that is the highest level of fetal hemoglobin upregulation that we've seen reported preclinically. I'd finally point you to the error bars here, which are very narrow, and you can see how consistent and reproducible base editing is as a tool. So we're very excited about this result, and this program is now moving forward very quickly. And as a reminder, we will be going directly in phase 1 into patients who have every chance to respond to these base editors, making that first data set a really definitive one for this program. As I said, we're complementing that with our first approach to directly correct the sickle mutation. So here we're looking at position 6 of the hemoglobin gene. There is an A where there shouldn't be. That causes the cell to create a valine in that position, which is the amino acid that can cause this polymerization. So in this case, you'd really like to go back to a T, which would give you the copy that most of us have in this room. We can't do that yet with a base editor, but what we can do is an A to G change. And if we do A to G at this target site, we get another normal human variant, and it's called HBG Macassar. And so there are people in the human population who have this. They don't have sickle cell disease. It is a normal and functional variant. So this would now be the first time when we're editing these cells that you're actually getting rid of the sickle protein itself. So here's the editing result. We've been hard at work on these editors. This is a case where we did want to do some protein engineering to improve our editing capacity. And having done that, we've generated the data you see on the right, showing over 65% precise correction of the sickle mutation in blood cells drawn directly from a sickle patient, which was almost exactly the same as the clinical process we will ultimately do in patients. Again, this level of precise correction is unprecedented compared to what would be possible using nuclease technologies. So two very different but complementary approaches to treating sickle and beta thal in one portfolio, which we think makes us very competitive to treat this very important group of patients. So let me turn now to a very different story in cell therapy. So here we want to create CAR T cells. And as you know, CAR T cells have been a breakthrough where we engineer them to attack tumor cells in the body, and they have transformed the treatment of certain rare hematologic malignancies. That said, there's a clear consensus in the field that we need to do more. We need to make them more effective. We need to get them from what are called allogeneic sources, i.e. a normal healthy donor, rather than taking them from the patient themselves. That way we could treat many patients with just one batch of manufactured CAR Ts. We want to prevent what's called fratricide. So if your target happens to also be on a T cell, then you have the risk that your CAR T cells will attack each other before they have a chance to attack the tumor. So we want to block that target on the surface of our cells. And finally, we want to navigate what's called the immunosuppressive environment. This means hitting things like checkpoints, metabolic pathways, exhaustion markers, other things that will basically boost the efficacy of these cells over time. So there's a long list of possible targets that we may want to knock out on these T cells. So in general, we can get 90% and up in our editing for really most or all of the targets we target within T cells. And you can see here that as we add edits, going from left to right for each of these targets, we don't lose any editing efficiency. So it's truly possible to stack these edits on top of each other. But now let me show you some very important data comparing this approach back to nucleases. So if you do this kind of editing with nucleases, you have two problems. So first, if you're making those simultaneous double-stranded breaks across the genome, the cell again won't know how to put those pieces back together again. And so you'll get these chromosomal rearrangements at these different cut sites. And that's going to generate novel chromosomes that is clearly undesirable when you're trying to generate the right kind of cell. When we do that with the C-base editor, you can see undetectable levels of chromosomal rearrangements. That makes sense because we're not cutting the double strand. On the right-hand side, you can see that as we add edits in yellow using a nuclease, going from 1 to 2 to 3, you're starting to lose cell viability. And by 3 edits, you've lost about 40 to 50% of your cells. Whereas when we do this with the C-base editor in green, you can see there's no loss of cell viability. Again, that's because of the damage response that's building up in the cells where the double-stranded breaks are being made and the fact that we don't make those breaks using base editor. So this is going to be a general purpose solution to highly engineered cells for a wide variety of applications. CAR T cells, NK cells in oncology and autoimmune disease, stem cells. There's really the entire cell therapy field. If we want to make a lot of edits, this is going to be a really important application. We're working very hard to think through how to exploit that and work with that industry to create a wide variety of new solutions for patients. In the meantime, internally, we're working on a couple of programs that we're very excited about that apply this sort of approach. Generally making allogeneic T cells to treat pediatric cancer populations. So these are kids who get leukemia. If they relapse after first therapy, they have a very poor prognosis and they desperately need new and more powerful therapies. So here we're targeting T cell ALL as well as AML. So on the right-hand side, you can see a result. We're showing the T-ALL program that we're working on. You can see 4 edits in each of these cells. each at 90% efficiency. You can see the cells in the upper right are very active in the presence of antigen expressing interferon gamma. And you can see the variety of functions that we've edited in using these edits listed at the bottom. So we think this profile of a product could be a powerful one to break through and create new treatment regimens for kids who really severely need them. Now let me shift over back to the in vivo side of things. So here we're delivering using LNPs, lipid nanoparticles. This is a very scalable, transient delivery modality. It's clinically validated. We have several proprietary formulations of our own. You can see here a mouse experiment where we're editing in the liver of these mice. You can see 60% conversion, again, of this specific A to G in this test site. And by the way, at a very low dose, 0.1 mg per kg, which shows how potent the base editor can be. And that bodes well as we move into higher order primates, as well as ultimately, of course, patients. So there are two applications that we're pursuing initially. The first is called alpha-1 antitrypsin deficiency. So this is a very severe disease with really a lack of therapeutic options for patients. So patients here can't make enough of this protein called alpha-1 antitrypsin. So this is supposed to be made by your liver and circulate through your bloodstream. If it does, it can then protect your lung from degradation. But in lack of it, your lung will gradually deteriorate, and you'll get emphysema, and gradually patients with this disease can require double lung transplants. At the same time, the mutant protein is building up in the liver and creating toxicity. And so over time, you also get liver failure and can even need a liver transplant. So you have both a lung and a liver insult to deal with at the same time. So in this case, you could do gene therapy to try to replace the protein in the bloodstream, but you require very high levels of the protein, and of course you wouldn't be addressing the liver problem. You could also do knockdown in the liver, but now you're not going to help with the lung, and in fact you may make it worse because you're going to further lower the bloodstream levels of this protein. So really it's a situation where ideally you'd want to edit. So that for every edited cell you're going to both secrete the normal protein and not build up a toxic protein in the liver. And the edit you really want to do is a base edit. There's a single A that causes this disease, and you want to turn it into a G. So a very prevalent disease. There's about 60,000 patients, all of whom have two copies of this single point mutation, E342K, that does look editable with our technology. So this is an example where showing variant 1, we actually started with relatively low efficiency based on the way the CRISPR was binding to the target site. But rapidly over the course of about 6 months, we were able to engineer both the CRISPR and the deaminase in our base editor and rapidly improve that activity to the point where now in this cell experiment you can see 80% precise correction of that A into a G. So really excited about the application and promise of this approach to create a potential one-time cure for patients with alpha-1 antitrypsin deficiency. The second approach we're taking in the liver is targeting glycogen storage disorder type 1A. So this is a rare orphan disease that begins in children and ultimately, of course, adults as well. And in this disease, you can't reprocess what's called glycogen, which is how your liver stores energy to enable you to fast. And as a result, you have to constantly take in glucose to maintain your blood sugar levels. And in fact, if you don't, you can die of fatal hypoglycemia, including overnight. So it's a very scary disease. Patients have to wake themselves up every few hours, make sure they're feeding, and then they can try to go back to sleep. So it turns out that we can actually base edit both of the most prevalent point mutations in this disease, R83C, Q347X, again, both correctable with a single A to G change. And you can see on the right, we can deliver about 80% correction and 60% correction of each of these mutations, again, which would cure these cells. Now, by way of comparison, there is a gene therapy in this application to the liver to try to restore function. But there's two issues with that. First, this would certainly be an indication where you would worry if the AAV gene therapy signal were to wane over time. You would never want in this disease to fall below a critical threshold of activity and then be exposed to hypoglycemia again. Furthermore, this is clearly a place where you'd really like to treat as young as possible, infants or very young children. And there, again, AAV gene therapy is not going to pass on as the cells divide and the child grows, so that signal will get diluted during growth, limiting them to really treat older children. Whereas a base edit, that edit is going to get passed on to each daughter cell as the child grows, enabling us to treat, hopefully, very young children. So So now the last story I'll tell you is in the AAV field, viral vectors. So here, of course, you're very familiar with AAV from the explosion of gene editing technology and gene therapy programs that are out there now. So in this case, as with some CRISPR applications, our editor is a little too big for a single AAV. But we have a very important workaround to that. So what we're actually able to do is take the editor and split it into two parts, two halves, put each of those into a different AAV, and then co-dose those AAVs. And it turns out there's something called an intine, which is just the name for the domains that then rebind the halves once they get in the cell and reconnect them. This turns out to be very efficient. It's a natural technique that we're taking advantage of. And you can see here that using that two halves connection is as efficient in editing as just transfecting in the full-length editor. And this allows us to now dose these using AAV, initially to the eye, to the CNS, and over time thinking about muscle, the heart, and beyond. So initially, we're applying this for an important disease called Stargardt macular dystrophy. This is the most common genetic macular degeneration. And in macular degeneration, you're basically gradually losing sight in the center of your vision, eventually causing blindness. So here we can target the most prevalent point mutation in this disease called G1961E. And here on the right, you're seeing a very exciting result where we're dosing that split AAV system onto actual retinal cells, so eye cells, at real-world viral doses. And you can see here over 50% precise correction of the point mutation that's causing this disease. So this is a really exciting therapy, would be the first of its kind. This is a case where gene therapy has really struggled because the gene you need to deliver in this case is much larger than a single AAV. And so unlike some other applications in retinal disease, you can't just put that gene back in using the AAV. So hopefully I've given you a flavor here of the very large diversity of different programs and different kinds of therapeutic edits we can create. In each case, with these levels of precise correction that are really unprecedented compared to what previous technologies are able to deliver, and what give us the confidence that this is a really important next generation gene editing technology that we're advancing. Now, around base editing, we do have additional tools to work with. We actually have a family of nucleases called Cas12b, so we can make that cutting style of edit if we ever need to. That also gives us another platform for targeting base editors. So every different CRISPR family gives us a different targeting element to create base editors. We have RNA editors as well. So these actually target RNA strands instead of DNA. And then we can, again, do that same base edit at that layer as well. And finally, we have access to a new editing technology called prime editing, which may allow short-range rewriting of certain gene sequences and would be highly complementary to what we're developing with base editing. So around these various editing technologies in our platform, of course, you've seen the different platform capabilities we've built, from computational biology, off-target biology, structural biology, and even molecular evolution to continue tuning and improving and optimizing these systems. Of course, you've seen the various delivery modalities that we're building internally, so we really control the ability to create medicines out of these editors. And finally, we really are building end-to-end capabilities in development. This includes process and analytical development, preclinical and clinical development, and more recently starting to build out GMP and quality to really make sure we can turn this from a very exciting research technology into a true new class of medicines that can treat a very wide variety of patients. This is the Beam team. So joining me today, in addition to myself, we have Pino Ciaramella, our President and Chief Scientific Officer. He came most recently from Moderna, where he started their therapeutics vaccines group and filed over 10 INDs while he was there. Previously, he had been at Pfizer, where he led the group that filed Maraviroc, the first cell entry inhibitor for HIV. We also are joined by Terry Ann Burrell, our Chief Financial Officer, who joins us from JP Morgan Chase, and Courtney Wallace, our Head of BD and Strategy, who joins us from Celgene. Along with the rest of the executive team you see here and our scientific leadership, we have collectively filed and approved 13 products and filed 70 IND filings. This is a point of great pride. We really think of ourselves as drug developers. And for us, the finish line in this effort is to get products approved and get them to patients as quickly as we can. And again, to establish base editing as effectively an entirely new class of medicine for patients. So it's been a very busy few years for us. We started in 2017 shortly after the publication of these base editor systems first occurred. In 2018, we closed all of our foundational licenses with our academic institutions and got the platform established. By 2019, we had gotten this portfolio moving in parallel, started to generate the data you saw here, and established feasibility with all three of those delivery modalities, showing that base editors could be successfully delivered. And culminating in vivo proof of concept data that I showed you before for sickle cell disease that we published at the hematology meeting at the end of the year in December. 2020 promises to be even busier, so we do expect to have additional in vivo proof of concepts out of the portfolio and the rest of the pipeline over the course of the year, followed by potentially moving into IND-enabling studies as well. If we do that, that sets up the potential for the beginning of what will be a wave of IND filings starting in 2021 as we move to the clinic. And as a reminder, if you remember that portfolio, this isn't going to be just a single program that moves forward. The idea here is to start to file multiple INDs as we go, and that's the parallelism of this portfolio strategy playing out. A big part of that is just looking to the future, how scalable this technology may really be. So if you think about where we're at with electroporation ex vivo, so we've established that in vivo proof of concept result already. So that means that that sickle program is going to move forward now very quickly to the clinic. As a reminder, these are all precision medicines where in phase 1 we're going to be treating patients who have every reason to potentially respond if we're successful, and that early data set will then be a definitive, hopefully proof that we have something very promising for patients. At the same time, it gives us confidence that we now know we can base edit blood cells very successfully. That means that any on-deck targets that we have can now move forward with a higher probability of technical success and a much faster process. Again, as a reminder, to create program number 2 or program number 3, we may be changing as little as that guide RNA, simply swapping out that element in the system, and you have an entirely new medicine. That will also be true in the in vivo programs for lipid nanoparticles and AAV. Once we establish that key in vivo proof of concept, in this case editing in non-human primates, we then know we can successfully edit that tissue and we can double down in that area and move on-deck targets forward very quickly. So this all means that the scalability of what we're doing will be very high. Once we achieve initial success with a given construct, we'll be able to rapidly follow that and expand our efforts towards many more diseases. So hopefully I've given you a sense of our excitement about this very unique next generation technology in gene editing. And the fact that around that we've built a very experienced team, integrated capabilities, and IP leadership. The engine is now already delivering very differentiated therapeutic programs across all available delivery modalities and has led to a portfolio now of wholly owned base editing programs moving rapidly towards the clinic. And all of this is in service of our goal to make Beam the leading company in precision genetic medicine and to make a transformative impact on patients' lives who are desperately waiting for new solutions. So with that, thank you very much for your